Michaela tried to.
Turning it on? Oh, that helps. Okay, thank you. Okay, welcome to the club meeting this night for August. It's great weather outside, good time for a telescope. But the show we just saw on the creation of the Earth and bringing it up to present status was really great, wonderful show. Does anyone out there remember their 9th grade science for what ATP stands for?
Adenosine triphosphate.
Good. I was waiting for them to say it in the show, but they never did. Adenosine triphosphate. That's what takes the energy in your body and makes it available to the cells. When you're tired, you run out of ATP. Okay. So anyway, welcome to the show. We're going to go through very briefly some business, and then we will get to our speaker who's going to tell us about habitability of planets, which sounds like terraforming to me, but we'll see. First, we're going to hear from Pat McPartland, who is our treasurer, but she's not going to go over our financial situation. I don't want anyone to break out crying. And but she's going to go over our merchandise.
Thank you, Jerry. Thank you. I didn't know I had a fan club. I'm a merchandise manager, and as you can see, I brought my full inventory tonight. Unfortunately, in the clothing, I don't have any more mediums, but you're more than welcome to try anything on that looks like it might fit. The other thing is I help the secretary by making name badges, and if you're a member, please look in the little index boxes and be sure that I've spelled your names right, or if you like to be called Bob instead of Robert, or whatever, let me know. And what else? If you have any requests or questions, you can reach me at merch manager at SBAU.org. Back to you, Jim.
Thank you, Pat. And now briefly we will hear from her husband, who will go over the outreach for the club. The newsletter went out by mail a few days ago, and the outreach stuff is in there too, but we're going to go over it again.
Thanks, Jerry. We got a nice, busy month. Tomorrow night, we're at Kachuma Lake with a slideshow, hopefully, and telescopes. We've had a little trouble getting the power on in the Fireside Theater, so sometimes there's no slideshow, but I've been assured it'll be on this time. And then, it's not really outreach, but early Sunday morning, between midnight and 4, if you want to get a picture of the shadow of Titan passing over the ball of Saturn, there's a chance to, a little photo op there. And then on Tuesday, the 5th, it's Telescope Tuesday, first Tuesday of the month this year, and out at Camino Real Marketplace, starting at 7 o'clock. And then on Friday, it's Refugio State Beach. And then next Saturday, the 9th, we have our planning meeting at 4, which will be on Zoom. And then we have our star party here at the museum from 8:30 to 10. And then, what do we have? Oh, in the mornings of, again, not outreach, but on the mornings of the 11th through the 14th, if you're an early bird, get up before dawn. Venus and Jupiter are going to be having nice conjunction in the morning sky, so super bright. Wednesday, we're at Carpinteria State Beach. Friday, The 15th, third Friday of every month, is Westmont's Public Telescope Night. Then on Saturday the 16th, we're back at Kachuma. And then on Friday the 22nd, we're up at Los Flores Ranch Park in Santa Maria with a star party there. It's fairly dark. And then on the 23rd, again Saturday, it's Kachuma. And then Friday the 29th is back to Refugio State Beach. And then on Saturday the 30th, back to Kachuma again. So that's it. There's a bunch of propaganda here. If you like star maps and moon maps and webpage listings and bookmarks, feel free to graze. Thank you.
Thank you. Now, Ronnie Herron will round out, not now, Ronnie Herron will round out our speaker introduction, but that's the officers. We're now going to hear from committee heads if they want to say anything. We're going to start with Tessa, our secretary. Do you have anything you want to say?
Pat, do we have any member directories here tonight?
Yes, we do.
We have member directories for members, $1. They're going fast. Get them now.
Thank you, Tessa. And now our event coordinator, Diane Welkenbach. Do you have anything you want to add?
Just that we're going to have the Kachuma Lake Campout in October 24th to 26th, and you can sign up to attend that. That's all.
As a matter of fact, if you sign up for that, then we'll have enough food. We host a dinner on Saturday night, and it's a camp out Friday, Saturday, and Saturday night for people who want to stay overnight with their telescopes. But if you just want to come up and pal around and chew the fat and the country meat market fair, you could just come up for the meal on Saturday. It's a lot of fun. Usually people bring lots of desserts and brownies and cookies. And then last but not least is Tom Totten, our equipment coordinator and of course webmaster.
So we have a few equipment you can see on the screen there. That's a small amount, but there's a bunch of telescopes and equipment. So if you're looking for something, let us know and see if we can get you set up for a reasonable price. Thanks.
What size are the scopes?
12-inch and 5-inch and 8-inch and yep, they're different sizes. So.
Why don't we take bids?
Yeah, eBay it is. Okay.
I'm sure he'll negotiate with anyone that wants to bid.
All right.
Thank you, Tom. I think I've covered all the people that have asked me to give a talk. So we're down to now, Baron. By the way, I saw John Palmentary interview the Baron on the news channel last night for the Fiesta.
About fell off your couch, didn't you? I was eating taquitos and didn't know the camera was on, Jerry. That's a once a year tradition, I think I told you that.
Yeah.
I didn't even want to go, but the guy comes and gets me in his Cadillac. There we are at the Mercado.
It's nice to be a VIP, huh?
Don't ever forget that. I'm a heartbeat away from your job. But we love these jackets. And our man is here. He drove over with his wife Teresa, Stephen Kane. We'll get to him in a minute. Steve, you want to raise your hand so we'll know? Oh, he's up there. Okay. He's got my cup that I'm supposed to give him because he needed a glass of water. And I said, I'm going to give you this porcelain priceless cup later. And here, I give it to him. So I do have something else to add to that. And he's going to be driving back tonight. And this is going to be a good one. I'm glad we're in the big theater here. We have a weekly vlog I want to talk about real quick. It's on Monday mornings. We've been doing it 4.5 years. Chances are Tom's got it on the screen already. It's called the SBAU Astro Hour. There's 6 of us. I get to MC. I'm sort of like the little boy in Mr. Wizard's Funhouse Saturday mornings. For those of you who remember the 50s. Gosh, Mr. Wizard, that's amazing. That's me. That's my job as interviewer. And President Jerry is the man that comes up with the talking points. And Tom Whittemore joins us. Chuck McPartland is there as our fact checker. Tom, incidentally, graduated Westmont. And is Tom here? Tom Whittemore? Okay. Bruce Murdoch. You want to there you are. And he's also president of the Theater Organ Society, that big organ inside Arlington. Once a month, you want to cram in there. And Tim Crawford, Tim didn't join us this month, did he? He's watching online. In fact, these people that get to see the Zoom show are home and I guess don't hear your questions or your reports when they throw it to the audience. But I've started using this, and I'm going to be using this to get your questions of Dr. Kane later on. So, without that, behind me I want to say that we're a fun club, not only because of the fun people that are in here, but it's a fun science. Of all the sciences, nothing's more fun than astronomy. You walk outside at night, look up, you're suddenly an astronomer. And you know that, otherwise you wouldn't be here. But I really would like to appeal to join us. It'll cost you about what it costs for a drink over at Harry's, $20 for a year. And we do get together and do things and have fun, and we could certainly use somebody if they have secretarial skills. Or maybe a bank teller or a CPA. We could probably use a new treasurer in the new year to take the load off our merchandise lady, because she's doing the treasury work. Come over here and you can find in Chuck's stuff over here the sign-up sheets. Future speakers, let me tell you who's coming to town. Ish Call. I think he's East Indian and he's going to raise his hand right now. There is our next month's speaker. Ish Call. It was hard to get to because he's very busy as a graduate student. When do you think you'll have your doctorate, Gish? How many years?
2 more years.
2 more years.
2 more years.
And the title of his talk, you're going to have to ask him later. I have no idea. It's called Galactic Atmosphere and Rain.
Yes.
Somebody said it was about Titan's atmosphere or the lakes of methane, and I thought maybe it would be about nebulae or whatever. Nevertheless, we're looking forward, and I invite him, and thank you for coming. Ish will be here Saturday night, or Friday night, September the 5th. October 3rd, we did it. We got an old Santa Barbara boy coming back from his esteemed place of work nowadays up at Berkeley. UC Berkeley's Filipinko. Is that on the stage? On the screen? Yeah, Alex Filipinko will be here on this very stage the night before his Dos Pueblos High School 50-year reunion. That's part of the reason we got him. UC Berkeley. I see him on as many YouTube videos as I see Neil deGrasse Tyson or Cox, the guy from Britain. November 7th, another great astro speech on a NASA program called SphereX. Maybe you've heard of it. I have not. I haven't looked into it, but he just spoke back in May to the $50 a head fundraiser for Mount Wilson. May 10th, he gave a speech on whatever he's doing for NASA. His name is Phil Korngut, K-O-R-N-G-U-T, and he's professor at Caltech. He'll be here on the night of November 7th. December 5th is our club's yearly in-house members-only science talks, featuring one person who's had some articles, 5 of them published in Astronomy magazine. He's not here tonight, but David Grossman is a good friend of mine. He used to run the Symphony for many years, and before he came to town, back in the late part of the last century and the early part of this century, he ran the music department at Paramount Studios. And he's a good friend of Luke Swetland, who runs the museum here. Luke was here earlier. They come to Saturday night star parties. David will be one of those 2 speakers, probably talking about what he wrote about on a cover story in astronomy about sonification, sounds in space. Even though you're not supposed to see those exploding things, those Star Wars things, but we sure hear them on the screen, don't we, in Star Wars. The other program, part of the program, the other half of the hour, will be our own Tessa Flanagan, who's stepping down as secretary in the new year. And Tessa will update us on, what is it, dark energy?
Yes.
Okay, and it keeps changing, doesn't it? New stuff all the time, research. However, right now, ladies and gentlemen, Dr. Stephen Kane, Planetary Habitability in the Solar System and Beyond, Professor of Planetary Astrophysics at the University of California, Riverside. Come on up and I'll read about you as you're walking up the street. topics, and he's discovered hundreds of planets orbiting all kinds of other stars. He's a leading expert on the topic of planetary habitability, obviously, the habitable zone of the planetary systems. I guess that's Goldilocks, right? And the study of why Venus, he's an expert on Venus. It's where he and his wife, Teresa, go on vacation. Venus and Earth were sister planets undergoing divergent evolutions. Stephen published hundreds of peer-reviewed scientific papers as well as several books on the topics of exoplanets and habitability. He's also been a prominent scientific leader for several NASA missions designed to search for life in the universe. Stephen Kane, welcome, my friend. You want to hang on to that? Or I'll give it to you?
All right, we're on. All right, well, thank you very much. Thank you for the invitation to come here. It's a pleasure to be here. I'm aware that there is a fiesta going on, so I know what you all sacrificed to be here, and I appreciate it. And thank you, Ronnie, for this cup. So, as was just mentioned, I've been doing this work for a little while now. I've, for the past 30 years, been professionally studying planets, figuring out how to discover them, how to characterize them, and ultimately how to determine whether they may or may not be habitable. Prior to that, I don't know if you can tell from my accent, there still is a bit of Australia in this boy, even though I've lived more outside of Australia than inside now. But I grew up in outback Australia, and so when I was a teenager during the 80s, my interest was in planetary science, and in particular the Voyager 2 flybys of Uranus in 1986 and Neptune in 1989 were a great inspiration to me. But when I started grad school, which was in the mid-90s, it was a very fortunate time to be entering grad school, because although I thought that I would go into pure planetary science, another opportunity arose, and that, of course, was the discovery of planets outside of our solar system, which I thought, okay, well, here's an infinite number of planets that I could be studying, and so that's the direction that I went. And so, as I mentioned, what I'm going to be doing tonight is I'm going to be telling you about how this work has evolved and how it's led me to planetary habitability, and I hope to explain to you what that actually means, because it is the sort of topic where if you ask 10 different astronomers, you'll get 13 different answers, and we'll see how we go with getting there. But as you can see, we've discovered a lot of planets at this point. You could say more than 5,000 planets. We're actually more close to the 6,000 threshold, and that's not bad for a couple of decades' work. But there are many of the giant planets. They're easier to find. They're the low-hanging fruit. You could think of them as in trying to find planets around other stars. But you can see that it says here that there are 4% terrestrial. That doesn't mean that there's very few of them. In fact, quite the contrary. They are the hardest to find. And it's very clear to us at this point that we are just scratching the surface, that the almost 6,000 planets that we have found is a very, very small amount of the amount that are out there. In fact, at this point, myself and many of my colleagues are convinced that all stars have planets. That is a natural consequence of star formation to have planets in orbit around them. So what we wanted to do when we moved from the 90s into the 2000s, when we were only finding planets like Jupiter at that point, is we really wanted to find these elusive terrestrial planets. And so we designed an experiment to do exactly that. And in 2009, we launched the NASA Kepler telescope. And
This is a simulation of what that launch actually looked like, because we didn't have a camera poised to see this happen. But what this is showing is the deployment of the telescope, because unlike the Hubble, for example, which is in a low Earth orbit, the Kepler spacecraft was sent very, very far into space, into what was called an Earth trailing orbit, so it follows the Earth around the Sun. And the reason that we deployed it to that deep space location was so that it could stand continuously for a period of about 4.5 years at 170,000 stars. And the aim of that mission was specifically to determine how many stars out there, like our Sun, might actually have an Earth-sized planet. And it was enormously successful, because what it found was that there are tons of these planets out there. In fact, when we looked at our bias away from finding these kinds of planets, like I said, they're very hard to find, and we studied the statistics, what it showed us very clearly is that the occurrence of planets increases towards smaller size. In other words, small planets are far more common than larger planets, which makes sense intuitively when you think about, say for example, a pile of rubble. There's a few of the very large boulders, many more of the smaller boulders, many more of the rocks, and once you get to the grains of sand, you can no longer count it anymore. Turns out planet formation works in a very similar way. But another interesting thing that came out of the Kepler discoveries was this plethora of different sized planets. And what this is showing is, of course, we have Earth over here for comparison on the right. And in our solar system, Earth is the largest terrestrial object. The smallest gas giant is Neptune, and Neptune is 4 times the radius of Earth. And all of us have heard from back when we were in school that, oh, our solar system has 4 small planets closer in, 4 giant planets further out, and it's a gap in between. They're even grouped together. But is that gap natural? Is our solar system normal? Turns out the answer is no. Our solar system is not normal, that this gap in between Earth and Neptune that exists in our solar system in terms of size is very, very easily filled when we look at all the planets that we have found elsewhere. So what you're seeing here is Earth on the right, and then all the way over to Kepler 22b, which is twice the size of the Earth and is probably terrestrial. And what you can see from here is that these are artists' conceptions of what they look like. We don't actually have pictures of them, unfortunately, but there are very talented artists that work at NASA. And I sometimes word it as, we're using genuine, made-up pictures of these planets. And you can see that some of them seem to have kind of Earth-like qualities. Maybe they have oceans, maybe they're habitable, maybe they're not. And it seems to be in some way related to size, but at least we know that there are plenty of planets the size of Earth out there. It's one thing that you hear all the time when it comes to press releases for new planet discoveries. Earth-sized planet found. And that immediately evokes images of life. Okay? When people hear Earth-sized planet found. But you see, this is what keeps me up at night, because there is an issue with this, and I'm going to explain what that issue is with something that I call the parable of the 2 villages. Imagine that you all live in a beautiful village. It is a wonderful place to live, and everybody is able to go on with their day-to-day life. This is not Riverside, by the way. However, from this village, you can easily see the remains of another village. It looks like it was exactly the same size as your village, but now it's burnt to the ground. And you go around and you ask your fellow villagers, when did that happen? And nobody knows the answer. You ask them, how did that happen? And still, nobody knows the answer. Then you ask probably the most important question, which is, could that happen to us? And nobody has any idea. Now, of course, I am talking about Earth and Venus. We have a twin planet. It is the same size as us, more or less. And it is referred to as a twin because it is the same size and they were born at the same time and probably have the same material. They probably had very similar starting conditions, but they turned out completely different. Many of you are probably vaguely aware of how hostile the surface of Venus is, but let me just give you a brief summary of what that is. The surface temperature, average surface temperature, which is more or less uniform over the planet, is about 850 degrees Fahrenheit, which is the maximum temperature of my barbecue that I've been using this summer. It also has about 90 times the atmospheric pressure, which is equivalent to being a kilometre depth in the ocean, way below the safe scuba diving depth. It also has sulfuric acid in the atmosphere. So if you're on the surface of Venus, you'll be melted, crushed, and dissolved all at once. It is about as hostile an environment as we could possibly imagine. Why? Well, conventional wisdom was that Venus is 30% closer to the Sun, and that means it receives about twice the amount of solar energy than Earth does. That's it. That's the end of the story. Or so we thought. Because in recent years, we've been using more advanced climate simulations, which shows that isn't all of the story. It's more complicated than that. And this is where it gets into this diagnosis of this whole topic we call planetary habitability, because in order to diagnose this, you need to look at all the factors. There are many differences between Venus and Earth other than just size. For example, Venus rotates extremely slowly. It takes about 225 days to orbit the Sun, but 243 days to rotate. It's rotating slowly backward. Does that matter? Does that influence habitability? Yes, it has a huge effect on climate evolution. It has almost no tilt to its axis, which is what gives Earth its seasons. It has little to no surface subduction, plate tectonics. There's very little of that activity happening at the surface that we can see. It has a negligible magnetic field, and it has no substantial moon. Those are just a few of the major differences between Earth and Venus. And the challenge in something like planetary habitability is to look at all of those things and say to yourself, probably all of these had some kind of effect, but how do we weight them? Which are the first order effects? Which are the second order effects? And so on. How do we sort these things out? Well, a starting point, whenever we talk about planetary habitability, you probably hear people talking about oceans and water, and certainly that has been very, very important for life on Earth. And we just saw the Planetarium show, which scooped my entire presentation. No, I'm just kidding. Actually, it was a fantastic connection to this, because the water on Earth has been a profoundly important part of the story of life on Earth. And some people have even said that wherever you find water, you find life on Earth. I think there's a circular reasoning in that last point, because Earth has been, if I may put it this way, contaminated by life for almost 4 billion years. And so at this point, wherever you find anything on Earth, you find life. That's why we have to work so hard to decontaminate anything that we're sending to Mars, or certainly anything that we would ever want to send to the surface of Europa. It's very, very important that we decontaminate it from all of this life that's present here on Earth. It's hard. But that's not to say that water isn't necessarily important. It is, and that's why NASA has this mantra of follow the water. Here are a couple of reasons why you might consider that water is important. For example, hydrogen and oxygen, the building blocks of water, are independently extremely common. Water is very, very common. If you think water is common here on Earth, go to the outer solar system. Well, don't, but if you could, the outer solar system is full of water. There's water all over the place. We see it in the interstellar medium between stars. There is a lot of water out there. Also, water is a neutral solvent in which biochemical reactions can take place. Now, there are possible substitutes for that, but the third one is extremely important, which is that water is in a liquid state at fairly high temperatures compared to other possible solvents, which means those biochemical reactions will take place so much faster. These are just some of the reasons that you can bring to bear on this. How come water is so important? So, what this means is that although there are alternatives to water, water is by far likely the most common solvent in which these kind of reactions are taking place. So, one way in which we can define planetary habitability is the ability of a planet to retain surface liquid water. Now, this is actually extremely challenging, and this is where we can start to look at the differences between Venus and Earth. Because retaining surface liquid water is very, very complicated, because when my earth science colleagues talk to me, they say, the amazing thing about Earth is that it's had liquid water on its surface for more than 4 billion years. And when you first hear that, you think, oh yeah, okay, I guess that's kind of cool. But then you quickly realize that means it's maintained a temperature range between 0 and 100 degrees Celsius over 4 billion years when everything is changing. The planet is cooling, the atmosphere is changing as the planet degasses, around it everything is changing. The star is changing, it's evolving, there's other planets in the system. It's a very, very complicated system, and trying to maintain that balance for long periods of time is very, very tricky and very interesting. And so what we try and do, and this is what I do primarily in my research, is that I look at diagrams like this, which place in the middle the possibility that a planet has surface liquid water. And then I start to look at all of the things that would affect that being able to be sustained over a long period of time. And this is a diagram which is colloquially referred to as the planets are hard diagram. It was created by Vicky Meadows and Rory Barnes at University of Washington. And in this diagram you can see that what they have done is that they have split it up into 3 major areas. First, we've got the effects of the star. And you can have different kinds of stars, you can have different properties of those stars that is going to profoundly influence the evolution of any planets that are orbiting them. Of course, you've got the properties of the planet itself. How big is the planet? What is it made of? And what kind of orbit does it have? And there are many, many other pieces that go into that. And then, of course, the properties of the planetary system itself. And are there other planets that are in that system which are influencing? But what I'm going to do for the remainder of this presentation is I'm just going to show you an example from one property from each of these 3 categories. And I will say that this is a very, very simplistic version, because when you go down the rabbit hole, you can start listing out hundreds of these properties. But like I said, some of them will be first order effects, they will be extremely important. Some of them might be lesser effects, but they do influence over long periods of time. And so it's a really interesting puzzle to try and unravel when it comes to the situation of Earth and what made an Earth an habitable planet. So, first of all, let's look at the example of stellar effects. And this is extremely important. One of my favorite classes to teach is stellar astrophysics, physics because I referred to stars as the engines of the universe. And certainly stars usually are the primary contributor to what I call the energy balance of a planet. That means the amount of energy that's coming in and the amount of energy that's being radiated back out. Those two need to balance out, and it's usually the star. If you're curious why I say usually, well, sometimes it can be other things. There can be tidal effects, there can be other sources, the interior energy of the planet itself. But usually the star is the dominant source. And as I mentioned before, there can be all different kinds of stars, different colors, different luminosities. How many of you have heard of the Hertzsprung-Russell diagram? Many of you have. Well, but many of you haven't. I'm going to show you something which I think is one of the most amazing discoveries our civilization has ever made. I shouldn't have built it up that big. What I'm going to do is I'm going to take these stars, which are all at approximately the same distance in a cluster, and we're going to sort them out by colour. So what I mean by that is that we're going to move the blue stars over to the left and the red stars over to the right. That's essentially separating them out by temperature. The blue stars are hotter, the red stars are cooler. Then we're going to sort them by brightness. The brighter stars will be at the top and the fainter stars will be at the bottom. When you sort stars that are at the same distance on those two simple axes, you uncover something amazing. It is a pattern, a snapshot of the life cycle of stars, and showing how different stars change through time. And what you see is that along this axis right in the middle here, this is called the main sequence. This is where stars exist for most of their lives, and that's where they're burning hydrogen. They're turning hydrogen into helium, and our sun is kind of in the middle of that. Now, one thing to be aware of when it comes to planetary habitability is that not all stars are created equally. Not all of them have positive effects. In fact, some of them have very negative effects. For example, if we were to look at our very massive hot stars up in the top left, those are great because they produce an enormous amount of energy. So you'll have no problem with energy. But they don't live very long. To the tune of about 10 million years, and then they not just die, it's a catastrophic explosion that we call supernovae, one of the most energetic events that we witness in the natural universe, and obviously that truncates the habitability of any planets that are in those systems. So those are not ideal. They don't live very long and they destroy everything at the end. Now let's try down in the bottom right. These are the smaller stars, much smaller than the sun. We call them red dwarfs. And they have a really nice advantage, which is that they burn their fuel happily for many billions of years. In fact, many of the stars that we see in this category are as old as the universe. They've been living that long because the amount of fuel that they have can last longer than the current age of the universe. However, these small stars are also very active. They have a lot of flares, they blast the planets that are orbiting them, and that can have a very negative effect on planetary habitability as well. And I'll show you an example of how that can be detrimental to this whole process in a moment. But when we look at these different kinds of stars, this is what allows us to calculate the habitable zone. The Goldilocks zone, as Ronnie mentioned earlier. The habitable zone is a tool which is often used to try and diagnose whether planets in that system might be good candidates for follow-up observations to determine whether they could be habitable. Now, it's worth really emphasizing the caveats to this. The Habitable zone is the region around a star where planets can have liquid water on its surface given a dense enough atmosphere. That's, for example, like when somebody says to you, oh, wait a minute, the moon is in the Habitable zone. That doesn't make sense. Well, that's because it doesn't have an atmosphere. The concept of the Habitable zone requires that it has an atmosphere and that it has surface liquid water, which is also the reason why we don't extend the Habitable zone out to where, for example, Europa is, which has subsurface oceans. What this is really for is for target selection. In other words, we have very limited resources and we're trying to determine which of these planets have life. We need to choose wisely because, as I mentioned earlier, there are thousands of planets to choose from. Where do we start? Well, we start where we know life worked at least once. Cooler stars have a much more compact Habitable zone, which is shown in green, and then as you go to the hotter stars, then the Habitable zone becomes much more extended. And a good example of a system that falls into the really cool star category is none other than TRAPPIST-1. Some of you may have heard of that system. It's a very well-known system now, and this is a system which was discovered to host at least 7 planets. It could have more. But the interesting thing is that at least 3 of those planets are in the Habitable zone, in the green region. Now, you can see that this is actually heavily zoomed in. If we were to place TRAPPIST-1 in our solar system, it would look positively adorable. It's like this miniature solar system. It's tiny, tiny, tiny. Its star is about as small as a star can be. But the big question is, do those planets actually have conditions that might be suitable for life? And this is where I'm going to get into my second example, because this is where we need to start diving into the properties of the planet itself. How do we determine this? If we have a system like TRAPPIST with these terrestrial planets, which are actually similar in size to Earth and Venus, how do we determine whether they might be habitable? Well, this is where tools like the James Webb Space Telescope come in. James Webb Space Telescope was launched successfully on Christmas morning, I believe it was, in 2021. I stayed up all night Christmas Eve playing video games because I think the launch was at 4:30 Pacific time, AM, and I knew it would be easier for me to just stay up rather than get up. So, the launch was spectacularly successful. And as many of you may know, it had hundreds of points where it had to deploy various pieces of the hardware. The thing that made people the most nervous was the deployment of the sun shields, which you can see unfurling right now. Those were simply held under tension, and as it was on its way out into deep space, that tension was simply released and hoped that everything would go according to plan. And it did. It went so well that it saved a lot of fuel getting to its location, which is on the opposite side of Earth from the sun. And so, James Webb has been observing many of these planets for a few years now. And it's been very exciting. We've been very excited within the community to see what it's going to find. And of course, one of the very first targets we pointed out was TRAPPIST-1. We had to know. We had to know what was going on with these small planets and if they could be suitable for life. Well, how do we do that? Well, we can use a trick of the geometry when it comes to these kinds of planets, because for the TRAPPIST planets, they occasionally pass between us and the star. And when they do that, whenever the planet passes in between us and the star they're orbiting, the light from that star passes through the atmosphere of the planet on its way to us. And that means that that planetary atmosphere absorbs some of that light. and reveals the fingerprint of the composition of the atmosphere of the planet. It's an amazing trick that nature has allowed us to use in order to be able to do this. And so this is what we're doing with James Webb. We're pointing it at stars, waiting for an event for this to happen, and then trying to see if it might have conditions suitable for life. Well, what are we looking for? Well, ideally, we're looking for something like this. This is a diagram which shows the absorption features that Earth would produce if we were an alien civilization looking back at it as it passed between us and the sun, and it would absorb some of the light. What does it absorb? Well, it absorbs things like oxygen and ozone, and those have been largely produced by the biosphere on Earth. We've got presence of vegetation. We've got the blue of the sky, carbon dioxide, which can be related to things like volcanic activity. We've got cow farts appearing in the data, and water vapor. The suggestion that there might be surface liquid water. So, did we see this for TRAPPIST-1? What we did see, actually, was nothing. What I mean by that is, when we looked at the data for TRAPPIST-1b, the innermost planet, we saw what we call a flat spectrum. That means more or less featureless, without any of those absorption features that you saw in the Earth spectrum. And in fact, what we saw when we looked at one side of the planet looked to be a similar temperature to the other side. And what this indicates is that there is no atmosphere. And in fact, you can see this quote here from the abstract of the Nature paper in which this result appeared. It said the most straightforward interpretation is that there is little or no planetary atmosphere redistributing radiation from the host star, and also no detectable atmospheric absorption from carbon dioxide or other species. This was greatly concerning. So this work was repeated for TRAPPIST-1c, the next planet, and a similar result has been found. And I'll tell you that for many of the planets which we've looked at so far, which are planets that are orbiting very small, very cool stars, we've noticed that many of them have these flat spectrum, which can be interpreted as these planets having had their atmospheres stripped. What is going on here? Well, we always need to remember when we're looking at planets that may be 100 light years away, and many of the times we can't even see them, that we need to go back to fundamentals. We need to go back to basics. And that means turning back to our solar system to try and understand what is going on. What do we actually know about the way in which planets interact with their radiation environment? And a great example of that is Mars. So Mars is half the size of Earth, and it has about 38% of Earth's gravity. It has a much smaller magnetic field, and this has quite severe consequences for the survivability of the Martian atmosphere, because many of you may know that the Martian atmosphere is actually a pretty good vacuum. That's probably a little bit cruel, but the Martian atmosphere is about 0.6% of Earth's atmosphere, which is one of the fascinating things, by the way, of our solar system, because it means that on one side of Earth you have a planet that's about 1% of Earth's atmosphere. On the other side, Venus, it's got 100 times more, so you've got 2 orders of magnitude on each side for a total of 4 orders of magnitude of atmosphere. Anyway, that's just an aside. But why is that the case with Mars? Well, we have studied this quite a bit, and this is a simulation of the solar wind hitting Mars. This is a simulation produced by a wonderful NASA mission called MAVEN, which has been orbiting Mars for some time now and has been studying the interaction of Mars with the solar wind. And this simulation shows that the Martian atmosphere should be ejected at very high velocity, particularly during solar events. When they compared the simulation with the data from MAVEN, they found that it matched extremely well, and that we were seeing the Martian atmosphere disappear in real time. Now, to be clear, Venus and Earth also lose their atmosphere, but not nearly at this rate. The consequences of Mars both being much smaller than Earth and having a very little magnetic field have resulted in Mars losing its atmosphere. And what we strongly suspect is that what I mentioned earlier about the type of star, the cool star that is very active, may mean that planets around these kinds of stars can't actually hold their atmosphere, even if they're as big as Earth. So, with that depressing note, I'll move on to my third example, which is from the third category, planetary systems. And this is something which is of great interest to me, particularly when we go back to that question as to, is our solar system normal? Because for those of us who were in the planetarium show, we saw that Jupiter has had a profound effect on the evolution of our solar system. And what this is showing here, this is a wonderful animation which is showing different groups of asteroids that are within our solar system. And when I look at different groups of asteroids, I look at them as the leftovers from the formation of the solar system that is providing the building blocks from which the planets formed. And particularly when we move out to the orbits of Mars and beyond, as was mentioned in the planetarium show, Jupiter has had a huge effect on the main belt asteroids and in the amount of material that was left to build the planets. And so as we move out and we start to see Jupiter, then we have to wonder, does that matter? Does it matter that we have 4 giant planets, most particularly Jupiter, because Jupiter is more massive than all of the other planets combined. So Jupiter is the dominant planetary gravitational mass within our solar system. And so it has had a huge effect. But what effect has Jupiter really had? Well, this is where we need to consider Jupiter as the friend or the foe. Now, does anybody recognize this picture? Shoemaker-Levy 9, of course it was. And I remember, I think I was in third year of university when that happened, and all of the telescopes, including the relatively new Hubble Space Telescope, were pointed at Jupiter to observe this event as the pieces of Comet Shoemaker-Levy plowed into Jupiter and exploded deep in its atmosphere. And we saw the real power that these kinds of impacts can have. And we saw the power of Jupiter to take one for the team. Because that was in an Earth-crossing orbit. And Jupiter broke it into these pieces and altered the fate of this comet to its eventual demise. Now, Jupiter has had a very interesting effect on both the formation and the continued evolution of the solar system, because even after it formed and it was grand tacking in and then back out, it continues to stir up a lot of the material. And some of that material is good, some of it is bad. Some of it is good when it's delivered to Earth when Earth is still young, because it can contain water. As I mentioned earlier, there's a lot of water in the outer part of our solar system, and Earth wants that. We want that. And so we want it to be delivered, but we want it to be delivered early. If you start getting these impacts later on, well, just ask the dinosaurs. But if you have stirring up of material later on, then it can cause extinction events. But the interesting thing about this is that, well, do other planetary systems have a Jupiter? And the answer is no. At about the 10% level. What I mean by that is, from the surveys of other stars that have been conducted, we have determined that approximately only 10% of stars have a giant planet that exists in the outer part of the solar system where it can stir up that material. Only 10%. So what are the implications of this? The implications are, we are here, and this is where you try not to get too anthropic about this whole conversation, right? But we are here, Jupiter is here. Is that important? Would we be here if Jupiter were not? If you could do that thought experiment, let's just imagine Jupiter never formed. What the hell, let's just throw out Saturn as well. All right, so Jupiter and Saturn are gone. Now, if Jupiter and Saturn never formed, what would Earth look like now? And it's a very, very interesting question because it could have changed the distribution of the material profoundly. It would have, for one thing, could have meant that Earth would have formed a lot more massive, but it also would have changed the way in which water is redistributed throughout the whole solar system. And so that's why, just an example of why other planets in the system are so important to consider when we're thinking about what has changed Earth through time. Does Jupiter matter? And I would put it to you that actually I think Jupiter matters quite a bit. So, I want to finish up by going back to Venus. Because Venus is really the main object that I focus on when I do my research on planetary habitability, because, as I said at the beginning, we have two objects the same size, formed at the same time, under the same conditions, and then turned out completely differently. Why is that the case? And I think the answer to that holds the key to really understanding how planets evolve through time and what their eventual fate is. And part of the reason that that's so important, because as I mentioned in that parable, we don't know when it happened, we don't know how it happened, we don't fully understand, therefore, if it could happen to us, and this is particularly important when we consider that Venus probably once looked like this. If you only look at the solar system at its current age, 4.5 billion years, you're ignoring almost everything the solar system has to teach us. Because as little as about 1.5 to 2 billion years ago, you were an alien civilization. You would have looked at our solar system and you would have seen that. Now, here's another mind-blowing thing. If you were in a spaceship orbiting Earth 2 billion years ago, you would probably look down at it and say, I wonder what planet that is. You wouldn't even recognize it. Earth of 2 billion years ago was not an Earth-like planet, which is kind of a profound thing. All of this to say is that the axis of time is crucially important in this. Try not just understanding where things are now, but how they got there and where they're going. Because going back to the example of the TRAPPIST-1 planets, there is a crucial piece of information I did not tell you. That planetary system is 8 billion years old. It's almost twice the age of our solar system. So what does that mean when we look at those planets and they don't have any atmospheres anymore or are otherwise uninhabitable? It could just mean that that's the way they ended. Not that they were never habitable, but that is the way that the story ended for them. And so that is a crucial piece for this. So understanding Venus is a huge passion of mine, clearly, and I've been working with NASA for many years on developing missions to go back there because it has been woefully ignored by our space program. We kind of went there in the 60s, 70s, and the 80s when we were competing with the Soviet Venera program, but then when we realized what the surface was like, it's like, nah, this is kind of hard. Oh, there's Mars. And so that's the way it went ever since, and I love Mars, but Venus is our twin, and we know almost nothing about it. We thought we did, but we don't. The good news is we're going back. And it was in the middle of 2021 that NASA announced the selection of 2 new Venus missions, which are going back to Venus. And it was a process where it was competing against a mission to Io, one of the moons of Jupiter, and Trident, which was a flyby of Neptune and Triton, which would have been great, actually. But it was time to revisit Venus and finally figure these things out. We can last a lot longer on the surface now. There's a lot of things about the surface and the atmosphere, especially the deep atmosphere, that we don't understand. So Da Vinci is the NASA mission that I'm on the science team for. It is an atmospheric probe which is going to descend down through the atmosphere on a 45-minute descent, and it is going to make it to the surface. It is going to measure with great precision the temperature, the pressure, the composition, and chemistry, all the way down to the surface, so that we can model the atmosphere and actually figure this out in the lab. So that will be profound. And the Veritas mission will be mapping the surface of Venus at very high resolution, so that you can go to a Google Venus website along with Google Maps. No, so that we can understand whether there's any geological activity that's still going on the surface of Venus, which is an important part of its evolution as well. So, obviously, in this presentation, I've only been able to skim over the surface of a great many topics. But there's a whole lot more to add to this. I've just got here as my summary slide, just a couple of other questions that I occasionally think about, and you probably have many questions of your own, and I greatly look forward to hearing them. So thank you very much for your attention. I appreciate it.
Which means we got time for Q&A, and I know there's some questions here. Ladies and gentlemen, there are people at home watching, members of the club on Zoom, so this way they can hear your question. Raise your hand. Hey, the president. Oh, I'm going to follow you probably. Okay. Thank you.
You mentioned the planned NASA missions to Venus. Are there any plans to float something in the atmosphere?
Oh,
That's a great question. Yes. So there are no such missions that have been selected at this time, but those mission proposals are in a fairly mature state. A colleague of mine named Paul Byrne, he has proposed a mission called Phantom, which is a balloon system that will essentially just, and the great thing about a balloon, by the way, is that you can have a fairly long-lived mission that will study the middle atmosphere of Venus over a long period of time. As you might imagine, the middle part of the atmosphere is where you might start encountering some of the sulfuric acid, and so you need to make that the blue material out of very, very special material. But those plans do exist, and I hope to see that happen.
while we wait for you to raise your hand, I'm going to ask my question real quick. There's a scientist named Drake who came up with a formula. How much of your stuff jives with his? I don't recall him saying anything about a Jupiter-sized planet may affect life on another, but are you together with him?
Yeah, so I talk to my students about the Drake equation quite a bit. And many of you may know that Frank Drake's famous equation has a very interesting history surrounding it, because he essentially came up with it when he went to the very first SETI symposium as a conversation starter, because those of you who have seen the Drake equation, it multiplies a bunch of probabilities together. The rate of star formation and the probability that a star has a planet, the probability that a planet it could be habitable, and the probability has life, and all these different things multiplied together. Now, some of these we obviously just have to speculate on, because as you go to the right-hand side of the equation, you start seeing probability that it has an intelligent communication that can, civilization that can communicate across space. Obviously, our constraints on that are pretty poor, but we do now know that there's around about 50% of stars have a terrestrial planet in the Habitable zone, which is one of the earlier parts of the Drake equation, which there was no answer to at that time when Drake put it together. As I said, that equation was really intended to provoke discussion. And so, although there are hundreds and hundreds of other factors that you could put in there, the probability that it has a giant planet like Jupiter, for example, as you mentioned, it's really just to start that conversation to lead us to a list of questions like this and many, many others, I'm sure.
Yeah. Okay, hang on, we're coming.
Hi, thanks for the nice talk, very interesting. I have a question. Why? Is there any theory that explains why Venus doesn't have a plate tectonics? Because that would change the game, no? For Venus.
Yeah, that's a great question, because when I mentioned earlier about the challenge in Earth having temperate conditions over most of its history, there's several key factors that come into that, and one of the most important, myself and I'm sure many of my colleagues agree, is the ability of Earth to sequester carbon from the atmosphere. What that means is draw it from the atmosphere, dissolve it into the ocean, and then store it away. And that's what we call the carbon-carbon cycle on Earth. And it's something, obviously, that we're now disrupting through human-based emissions. But this is a natural process which Earth has been able to use as a thermostat to regulate the amount of CO2 that is in Earth's atmosphere, which is, of course, a very strong greenhouse gas. So that is very, very important. And so when it comes to Venus, an interesting question there is a cause and effect. Did it lose plate tectonics and therefore lose the ability to regulate its atmospheric CO2, which built up and then it moved into a runaway greenhouse? Or did it transition into a runaway greenhouse which evaporated the oceans, which act as a lubricant for the plate tectonics? It's a really interesting chicken and egg problem, and it's one of the ones that is definitely a big question of Venus for when would it have lost plate tectonics, if it ever had. Because if even for Earth, the history of tectonics on Earth is constantly under debate about the extent to which there's been tectonics, if there were periods when they essentially paused and then came back. It's a very interesting problem.
I have a question down here, and then we'll head in the back.
Thank you. Hello, Dr. Kane. You know, you made some really compelling points about the habitable zone and what would really qualify us for it. And in a way, I know it would be intrinsic to it since obviously it worked for Earth, but I really think that all the definitions are really Earth-specific to our system. And the main definition, there's liquid water, significant atmosphere, is much too vague. I really think that a magnetic field is necessary for the definition with that MAVEN demonstration you made to preserve the atmosphere. However, I think something really promising for a lot of exoplanetary systems is from the really latest research, just a few days ago actually, is the possibility of what they call a radiolytic habitable zone. Now, radiolysis is a process where cosmic rays impact water in any state, a solid, liquid, or gas. And it splits the hydrogen and emits a free-forming electron, which can power and energize all sorts of chemical reactions. And that potentially seriously expands the habitable zone to Europa, Enceladus, and even Mars, anywhere where there's cosmic radiation and water. In a way, an atmosphere is not even necessary. It could be subterranean water, where the water radiation, or solar wind rather, does not even really affect it. How do you think this could affect research? And is there any exoplanets that will need to be reevaluated with this knowledge of the radiolytic habitable zone?
Yeah, you bring up some really good points. I've been studying the Habitable zone for many, many years, and it has seen many of the kinds of things that you're talking about. And like, for example, the effect of planetary rotation. So the initial Habitable zone calculations that were carried out by Jim Caston in about 1995, and they're essentially very Earth-based. So let's put the Earth, a thought experiment, let's move closer, let's move further away, see what happens. But you can have different sizes of planets, but you can also have different rotation periods. You mentioned magnetic fields, that's also a good one. Now, the problem with things like rotation period and magnetic fields, and in particular rotation, because as I mentioned, there's a huge difference between Venus and Earth, which I think has profoundly affected their evolutions. And we can't measure it. And this is one of the important pieces of the Hubble zone. The Hubble zone is more than just a theoretical construct. It is an observational tool. It is a tool at which we can say, let's go there and look for it. Now, when it comes to magnetic fields, unfortunately, the magnetic field of certainly a terrestrial planet is something which is completely beyond our reach at the moment. We cannot measure the magnetic field, although there's been there's star-planet interactions, there's auroras, there's various other effects that could be measurable in the future, but for now we can't. We also can't measure the rotation rate, which I think is a huge problem, because I think rotation rate is a first-order effect. So the fact that we can't measure any of those potentially first-order habitability effects yet shouldn't deter us from A, figuring out how to measure them, and B, from looking anyway. And so the utility of the Hubble zone, as I said, it's not really a theoretical construct, although there's been many, like the ideas that you mentioned, but it's a tool for observers on what they can do right now in target selection. And that's the important part of it.
Okay.
Good points.
Who's back here? Come on.
Right here.
Okay, sir. You can stand if you want to, the young man can. You can sit.
Oh, he's the young man, but that's true. What was Earth like 2 billion years ago that we wouldn't recognize it?
Well, so there's mostly, so 2 billion years ago is kind of an interesting time because there was a lot of things happening there with things like the rise of oxygen and so on. But most of the reason that I mentioned that at that time is because there are two things that certainly would have been very, very different. That is the configuration of the continents and potentially cloud cover, depending on what was going on with volcanism at the time of Earth 2 billion years ago. So those would have been the two main things that I think people would look at it and really, really struggle to recognize it.
Questions? Behind you? Bruce?
Hello.
Take the floor. You don't have to stand up.
I'm going to reach the microphone that way.
One of the things, questions we get very often at star parties is, do you think there's intelligent life out there? And my answer is absolutely. One of the factoids we put out is that there are more stars in the universe than there are grains of sand on all of Earth, by order of magnitude at least. So if that's the case, coupled with what you just said about half the stars might have habitable planets around them, you know, the 5,000 number that you put up there, the decimal point's in the wrong place. Is there something wrong with that reasoning?
No, there's nothing particularly wrong with that reasoning. See, what I would say, as I mentioned earlier, I'm convinced, as many of my colleagues are, that all stars have planets. As to how many stars have planets in the Hubble zone, that's around about the 50% level. Now, then you start getting into the more complex parts of the Drake equation after that. You start having to ask questions about, well, what's the probability that life forms? What's the probability there's intelligent life, and so on. But more profound than that is all of the other factors which can come into play. Because if it's true that low mass stars, these tiny stars like TRAPPIST-1, if it's true that those do blow off the atmospheres of their planets relatively fast, then it means that most of the stars have been ruled out. They're off the table, which is sad. And that it could mean that we need to be focusing on a lot more like stars like our sun, or stars which are a little less massive, a little more massive, the Ks and the F stars. That might be the case. We're not sure yet. This is something that we're trying to figure out. because as I mentioned in the case of TRAPPIST-1, it's very old already, so we don't know what happened before. So there's still hope. But my guess for myself would be that in the same way that planets are a natural part of star formation, that life is a natural part of planet formation where the conditions for habitability have been met, i.e. sustaining the presence of surface liquid water. Whether that leads to intelligent life is far more unknown, I think. The ability to build a spaceship or radio antenna is not necessarily evolutionary favored, although you could argue that the invention of tools does prolong a species, but and inevitably lead to that. But it becomes a very interesting discussion after that. So to answer your question, that was a very long-winded way of me saying, no, I think it's all consistent.
Webmaster.
So my question is, do you think the transport of life through the universe, like water bears floating around, how that could seed the universe with life? What do you think about that?
Yeah, the panspermia idea has been around for a while, and there has even been the suggestion that there could be life that's transported from one planetary system to another. I think that's very hard, at least when we look at Earth-based life. Even the most hardy cases of life on Earth, when they're deprived of water, they can go into hibernation for something like 100 years or so, after which they perish. So it's difficult to maintain them for an interstellar journey. However, within the solar system, I essentially think that everything is compromised. Because the simulations that I have seen of impacts that have occurred on Earth, including the impact 66 million years ago at the end of the Mesozoic, including that, distributed material throughout the solar system, which impacted most bodies, including Europa. And so all you need then is for panspermia to be possible within a planetary system. And so that's why I always say that what's really important for us is to find cases of life outside of our solar system, because then you can start to say it's independent of ours, because if we do one day go against the wishes of Arthur C. Clarke and land on Europa and drill a hole and put a James Cameron-type mini-sub down there and find some weird-looking giant squid, the first question we're going to have is, does it have Earth-based DNA? Does it have a similar origin? And I think the answer to that could be profound for our own solar system.
Cute. Okay, up front. Got it? We all want to know about the UFOs, don't we? Are they here, Doc? Never mind.
So one of your earlier slides was talking about factors such as distance to the sun, rate of rotation, and direction of rotation as factors in planetary development. And my question is what role does direction of rotation play in planetary development, and how might Earth be different if it rotated in the opposite direction?
Oh, what an interesting question. See, this is where we're learning a lot over the past decade, or the past 2 decades really, because of the use of 3D climate models. See, back in the 90s, when we were developing things like the Habitable zone, those were what we call 1D climate models. That is, essentially, we calculate the amount of energy coming in, the amount of energy going out, we balance that out. 3D climate models allow you to include rotation and the tilt of the axis and all those kinds of things. And so a lot of people have started exploring this, the effect of rotation. One of the reasons, by the way, that we think that Venus could have been habitable in the past is because it turns out its slow rotation goes in its favor. Because if you're a slow rotator, even though you're closer to the sun, you can have a lot of cloud formation on the day side of the planet, which cools it and allows it to maintain surface liquid water erosions for a long, long, long time. Whereas Earth is always just mixing it up and mixing it up. If Venus had had Earth's rotation rate, it certainly would not have had that habitable period. But if if Earth was rotating in an opposite direction, that would just be really, really weird. But I don't think it would necessarily have an effect on the evolution of life, but it would have a profound effect on the climate evolution. And certainly, I haven't seen too many simulations which look at reversing Earth's rotation, but there are certainly a lot of simulations which look at tilting the Earth right over, for example, and having this dichotomy between a frozen side and a temperate side and things like that, or even cases where you only get life formation at the terminator zone, which that's not a reference to the James Cameron films. That's the region between permanent day side and permanent night side. We could have a temperate zone right, like in a ring around the planet. So you can get all kinds of weird configurations like that that are caused by the change in the rotation rate.
Any closing questions? One over here. Make it good. Oh, okay. David?
Do you think having free oxygen in the atmosphere means that it can have free oxygen in the atmosphere without life causing it?
Absolutely, yeah, and it's one of these realizations that the community has been thinking about through time. When we think of the Earth spectrum, like the one I showed, and had that particular absorption of oxygen and ozone, then that's got to mean life, right? But oxygen, you can't get a very oxygenated atmosphere produced what we call abiotically, which means without biological input into that. And in the case of Venus, for example, if Venus did have oceans and then it lost them, what happened to that water? Well, a lot of that water would have gone up into the atmosphere and it would have been disassociated by the solar energy into hydrogen and oxygen. The hydrogen would have escaped, would have been blown away the same way that we see from Mars, and left with a lot of oxygen in the atmosphere. And so one of the big mysteries for Venus is that if it did have oceans, where did the oxygen go? You can oxidate the surface to a certain amount, or you can bury it away in other geological processes, but it's actually really difficult to get rid of oxygen, which is being produced by non-biological processes. But you would have to have it in combination with something like methane, because if you put methane and oxygen together, they react very quick and produce carbon dioxide and water. And so if you saw what we call a disequilibrium, then you know that something is producing the oxygen, and you know that something is producing the methane, otherwise they would cancel each other out. So that's the sort of signature that we want.
Make it quick because the president's after you.
So, fascinating experiment studying the atmospheric absorption, very remotely. You gave a great example of TRAPPIST-1. Are there any planets that you've studied where you're like, yeah, check, there it is. There's the CO2, there's the oxygen, there's the water, check, check, check. Has it lined up and you've seen it on any planets?
So, carbon dioxide has been detected very strongly in the atmospheres of some planets, but those planets where it's been detected is, once again, unfortunately, been the low-hanging fruit, meaning giant planets. There are giant planets where we have detected CO2 because that actually, the absorption feature of carbon dioxide, one of the, for those of you who are familiar with the wavelength range that JWST uses, there's a strong absorption feature at 4.3 microns, which is right in the JWST. It's perfect. So we've seen it. We know that it works. We just haven't seen that for terrestrial planets. It's of great interest to me because one thing I'm interested in is how would you tell the difference between Venus and Earth? Would they look different? And because I want to know is, out of Venus and Earth, this is one of the fundamental questions for me. One of these two siblings, I suspect, is extremely weird. It could be Venus. We tend to think so, because, we're here. But it could be Earth. Earth could be the weird one, and Venus could be normal. And we would know this if we looked at a bunch of planets and we found that they all were in a runaway greenhouse state with strong CO2 absorption. That's the real goal there. And so one of the things that concerns me is if we look at a habitable planet or a Venus-like planet, can we tell the difference between the two just from the amount of CO2 absorption? But I'm still looking, I promise you, I'm still looking.
Okay, Gary?
One more question, and it's tricky because I don't remember what it is to ask you, because I've forgotten it. But about a year ago, or within the last year, there was an announcement that they had found a molecule by the technique you were just describing of the sunlight coming through the atmosphere of an exoplanet. And they found a particular molecule that is consistent, probably with life. The word for that molecule escapes me, but it wasn't one of the ones that I would normally automatically think of for life.
It was DMS, dimethyl sulfide.
Yes. How does that fit in with that planet fitting into your life scenario? Does it have a Jupiter in its system? Do you know anything else about it?
I was curious how long we would make it into the question time before somebody would ask about that. But because there's a very analogous situation that happened with Venus itself, because some of you may remember that a few years prior to that, there was an announcement of a molecule called phosphine that was discovered in the atmosphere of Venus, and the suggestion was that that could be biologically produced. And so essentially what we have here is a test, because this is a biosignature claim, signature of biological activity for an Earth-sized planet. Not only that, it's the nearest Earth-sized planet, third brightest object in the sky. If we can't get it right there, how are we going to get such a diagnosis correct for a planet that's 100 light years away that we can't even see? So the situation with phosphine is still very, very ambiguous. It's not secured that the phosphine has been detected, and it's certainly not secured that life is the only explanation for it. Very similar situation for what you described. The more recent case is a planet by the name of K218b. And K218b is about 2.5 times the size of Earth. And so it's a kind of planet that we don't have an analog for in our solar system, and so it's very difficult for us to know what it might even be like, whether it has oceans. They kind of, there are various models, some that have kind of a molten lava surface, which obviously would be inhospitable, but some which have a huge ocean as well, which could be produced in the DMS. DMS can be abiotically produced as well, and there's, I don't know if any of you follow the literature on this, but after that was announced, the scientific community basically all looked at the data and got all upset because, you know, nobody likes a grandstander or something like that, you know. So, but it is a very interesting detection, but it's still being discussed. But it's the same sort of thing as with the phosphine on Venus. The DMS is not secured in the JWST data. It's a very, very low signal to noise detection. And secondly, the biologists have immediately told everybody, you don't need life to produce this. So, interesting, it exemplifies the challenge that the community faces in trying to diagnose this.
Okay, quick question from Mike Hardwick.
You mentioned, where did the oxygen go? Go to the mic.
You mentioned, where did the oxygen go? Well, you mentioned that Venus has got a lot of sulfuric acid, H2SO4. So, I mean, that's a lot of oxygen combining, you know, with compound. Is there anything to that?
It's certainly part of that chemical process for sure. A lot of that is normally from the sulfur dioxide, because one of the interesting discoveries about Venus in just recent years is that Venus is volcanically active. We weren't sure about that before, but it was inferred because of the sulfuric acid and the possible component of the molecular oxygen in that reaction. But also the contribution of sulfur dioxide from volcanic outgassing from the surface. So that's another one of these interesting pieces, I would say, that we would learn a lot more if we had better constraints on the chemistry of the deep atmosphere of Venus. That would help a lot.
Dr. Kane, I don't take any of those points on the screen or in the Drake equation. I've been looking them over. And I may have missed a few points, so if I'm repeating something you brought up, I thought of a couple other things. Maybe you brought this up and I was busy doing something else. having a moon would ensure that we develop a big moon, one big moon that's, you know.
Right, this one right here.
Oh, that's in there, okay, I didn't read that far down. Having an axis that's tilted so you get seasons, would that help assure life involved in another world?
Yeah, it's another one of these anthropic things where we look at our habitable planet, we see the presence of a substantial moon, and we can be tempted to put the two together and say, well, you know, obviously they're related to each other, not necessarily. Moon did help in the emergence of life through the creation of tidal pools. The tides for the oceans producing tidal pools can concentrate bioorganics and accelerate those kinds of reactions taking place. But in terms of stabilizing the rotation and the obliquity of Earth, it's not clear yet if that's necessarily required. And in fact, one of the great theories for Venus, by the way, is that Venus also had a collision, and it also had a moon, and that moon ended up breaking apart and causing essentially an apocalypse on the surface, and then brought an end to its habitability that way. So it could be a double-edged sword as well.
And I learned something about water not long ago that I didn't know. Of all the substances, elements, compounds, water is a compound. Its solid state is lighter than its liquid state. That's why ice floats. And that would help, giving the fish time to build their lives underneath and not be frozen at the bottom of the stream. Do you suppose methane melts differently, or ices up differently on a place like Titan?
I don't know, but Titan is certainly a fun playground when we send Dragonfly there eventually. I'm looking forward to that.
So any place which has water has that advantage. Mr. President, we're going to close the meeting down, but I got to give this man one more gift. Tell you once again, next month, September 5th, on a Friday night, please come back for Ish. Is Ish still here? There he is. What the hell is your talk about, Ish?
It's about the atmospheres of galaxies.
Atmospheres of galaxies, of course. You know what that is, don't you? All right, I gave you your cup already so you can have a drink of water. That's a priceless piece of porcelain from dug up from the Chumash burial grounds in the back. This we're going to add from our big club yard sale over here. Please hit it on your way out. And thank you for coming. You've got to drive over the back.
Thank you, everyone.
That was beautiful. Thank you. Thank you, everybody, for coming.